Welcome to today's webinar. Today we'll be discussing challenges in analysis of heterogeneous samples, and we will focus on application of small area XPS and imaging tools for addressing those challenges. First, I would like to share with you a few examples that introduces the challenges. The first example shows a film on a glass. Presumably it's a homogeneous sample, and we would like to obtain average composition. We are using large area, which is 1400 micron by 100 micron area of analysis to extract atomic concentration. So here is the output, so we can have a look at the average and standard deviation. And we can see that even for elements that are present in really small quantities, standard deviation is pretty small. So the large area spectra show homogeneity with standard deviation in order of 5%. Therefore, we can consider this composition as a representative of the sample chemistry. The second example is very similar. We have a film on a glass sample, but in this case, the sample is heterogeneous. So when we acquire large area spectra, we immediately see differences in intensity of peaks in our survey spectra. And when we look at the standard deviations, we see that for some of the elements, the standard deviation is of the same magnitude as the actual concentration. So in this case, large area spectra points to heterogeneity with really large standard deviation, and therefore average composition cannot be accepted as representative of the sample chemistry. Some more deeper investigation has to be done in order to understand what is indeed we have at the surface. So here's an example of X-ray induced secondary electron image. In this presentation, we will be discussing a lot of SXIs, as we call them, and technology behind them, and application. So SXI is a scanning X-ray induced secondary electron image. This is the same X-ray beam as used to produce spectral data is scanned, and that generates secondary electrons, and we can collect them through spectrometer. And the intensity in these images is proportional to the intensity of the secondary electrons at a given X-ray beam position. So immediately, under 10 seconds, we can obtain these live SXI images, and we can see some bright areas and some dark areas. This contrast is induced by differences in chemical composition. So using small area approach, we can focus on those bright and dark areas. The size of these features is an order of 50 or 150 microns. So we can use our 20 micron X-ray spot, and we can obtain chemical composition from two different locations. And we can see immediately that on the bright spot, we have our film as expected, and on the dark one, we have just carbon. So without that additional imaging capability and without looking at the smaller scale, we would not be adequately describing the chemistry of our sample. So what is small area analysis? 20 years ago, a very important paper came out from Don Baer and Mark Engelhardt that discussed approach to determine area selectivity in small area XPS. And I would like to share this quote. There are times when the analyst is tempted to look into area as large as possible to increase the count rate so we can have a higher signal-to-noise ratio and to obtain average information over the specimen. But due to variation in signal intensities, due to variation in binding energies, and what's important, due to heterogeneity intrinsic to the sample itself, the signal obtained may not necessarily be average surface composition. When we plan XPS experiment, there are a lot of questions that we need to ask in order to decide what exactly type of data will be acquired. Last year, a set of practical guides for XPS have been published, and the first steps in planning and conducting is the paper that discusses these very important issues. Today, I would like to focus on just two of those questions that are related in us deciding whether we need to do large area or small area analysis. The first question is, what is our analytical objective? What information we would like to learn? 90% of the time, we just would like to understand what is the average composition of the surface, and we need to know for sure that it is representative of the sample. Sometimes we need actually to study whether the sample is heterogeneous or homogeneous. When we compare the treatment and modification to the sample's chemistry, we have to be sure that the changes introduced are statistically significant and they are larger than within the sample heterogeneities. The second question that we always need to ask is what part of the sample we would like to analyze. What is the part of the sample that is of interest? And what comes with that is the most challenging question is how can we ensure that we have chosen the proper area for analysis and that the signal produced is actually coming from the area of analysis of interest. And these two questions will determine whether we need to analyze our samples with large area or small area XPS. So how do we perform small area analysis? There are two different approaches that manufacturers use. The first is lens-defined approach. In lens-defined approach, the area is being flooded by large X-ray beam. But then the analysis area is being defined by the lenses and aperture system. As small as 15 micron area of analysis is possible using this approach. There are some disadvantages to this. The first is that due to restriction of the angular acceptance, we are not collecting all of the electrons. So in order for us to obtain spectra of significance, intensity, and signal to noise, we need to increase analysis time. The second disadvantage comes from the fact that we are flooding really large area of our sample with X-rays, while we are only collecting electrons from small area. So if we have X-ray sensitive samples, then we are inducing damage in the areas from which we are not even producing useful signal. The second approach, and this is the approach that all of the 5 instruments are used, is source-defined. So in this approach, we are using micro-focused X-ray beam, and that what determines the size of our analysis area. The size of X-ray source is defined by the electron beam that generates X-rays from the anode. In this approach, as small as 10 micron small area analysis is possible. The advantages of this approach is that we are operating maximum transmission, so we are collecting all of the electrons. So sensitivity is larger than in lens-defined approach. And the second advantage is that X-ray is confined to analysis area. So for X-ray sensitive samples, we are not inducing damage around the area from which we are doing analysis. And that allows us to create different strategies of rastering the X-ray beam or moving around, collecting from larger areas to mitigate the X-ray damage. The disadvantage of this approach is that when we are decreasing the X-ray beam, the anode power is limited. So we cannot really increase our power to increase the flux of the X-ray source when we are using smaller electron beam spot sizes. It's really important for us also to understand how to measure analysis area. So we are defining our small area by either lens approach or by X-ray source, but what is it indeed? There is a common method that is being used. So what we need to have for that is a sample with a really sharp edge. So silver knife edge sample works for this purpose. So when we're moving our analysis area across this edge and we're collecting intensity. So as soon as we start seeing the electrons, this is where we see the edge. And then as we move, we are coming to a plateau. At this plateau, our intensity is reached 100%, and now we are at the flat part of our sample. And now from this intensity distance plot, we can use different statistical ways to determine what is the analysis area. Different manufacturers use different approaches, but if you think of the statistics of sigma approach, if the response of the spectrometer and beam profile is represented by the Gaussian curve, then one standard deviation from the center of the analysis area will capture between 16 and 84% of the signal. So in order for us to really focus and get 100% signal from the feature of interest, we should work within 3 standard deviations. And that what determines the relationship between the size of the feature that you would like to analyze and the probe size or analysis size that you need to use for that. So the relationship is 3:1, and it's really important to remember when you are selecting the size of a X-ray or analysis area when analyzing small features. In order to determine the area selectivity, that you indeed are collecting only data from the specified feature of interest, dot test should be done. This is the illustration of this dot test. This test was also proposed in the same paper from Don and Mark. So here what we have is secondary X-ray induced images from tin solder balls that are deposited on the silicon substrate. So when we zoom in, we can just focus on one single solder ball. So we have tin on the ball, and outside areas are silicon. And we know from measurements and from specification that the diameter of the ball is in the order of 150 microns. So we can use different X-ray beam diameters and center it right in the center of the ball, and then collect the spectral data and see at which point we start seeing the signal from outside the solder ball. So here's the plot of silicon to P2S spectra. Basically, it's a signal that comes from outside the ball when X-ray is focused on the ball itself. So we see that around 100 and 200 microns, we are definitely capturing a lot of signal from outside. So this is the atomic composition obtained. So even at 50 microns, you see that we're still capturing silicon signal. So the dot test tells us to create the plot that is shown right here. So on the y-axis, we are plotting the fraction of the signal from inside of our feature, which is our tin, to the signal outside, which is our silicon signal. And on the x-axis, we're plotting the relationship between the size of our feature, which is 150 micron, and the X-ray probe size, or small area defined by lens approach. So here's the data point for 8 micron X-ray size, spot size, 20, 50, etc. Remembering our relationship between area selectivity has to be 3:1, so the ratio between the size of the feature and the X-ray size is 3:1. We see when we find this on intersection, we are capturing 87.4% of our signal. In addition to area selectivity, we also need to really understand what is the size of our beam. In multi-pack, we can do this measurement. This is our data reduction package. So we can extract the line profile from our SXi image and look at the intensity as a function of distance. And then we can select which method we need to calculate the beam size. As you can see, in multi-pack, there are 3 different ways: 80-20 intensity, 80-4-16, 80-8-12. So for 80-12-20, this green line is 80% of the total 100% intensity, and the second green line is 20% of the total intensity. So then we are using vertical lines on intersections to calculate the beam size. So it's really important for you to be consistent from day to day. So when you are tracking your instrument properties, beam size, specifications, you always need to report which way you have calculated the beam size and do that consistently. So now that we've discussed the way that we perform small area analysis and how do we know what is our X-ray beam size and how to measure it, let's look into several suggestions on how can we avoid misinterpretation. So the first is general multi-technique approach. We need to use complementary microscopic information. When customer brings you sample, ask whether they have SEM images. There may be a need to mark the part of the interest of the sample with some grid or fiducial mark so you know where to look at. We also have optical images that we can obtain using intracamera or chamber images. And the second is comparison of average composition using different probe size. This is something that has been underutilized, and it's really powerful. Comparison of standard deviations will tell you the degree of heterogeneity of the sample. And this is an example that I would like you to show. So here we have carbon particles with several silver defects on top of them. We have selected 10 areas for analysis, and we can see 700 micron field of view as secondary X-ray induced images. You can immediately see contrast, heterogeneities in these images, brighter and darker areas. Some of this is due to topography, but most of it is due to different concentration of silver. So in order for us to understand the effect of area selected for analysis on the information we obtain, we have performed the following test. So first, we used X-ray beam of 100 micron just to extract spectral information. That effectively corresponds to approximately 300 micron analytical area. And then we used the same X-ray beam of 100 micron, and we rastered over large area, 1400 micron by 100 micron. So this is our large area mode. And we compared the data between these two probes. So here's the output. So here we have a subset of 3 spectra with extreme largest and smallest silver concentration from large area and from small area. So immediately you can see that even from the survey spectra that the range of concentration of carbon is quite different for smaller probe size. So atomic concentration table shows that we have between 86 and 92% of carbon, and areas 1 and area 2 are quite similar, approximately 4% of silver, and well, area 3 has really small amount of silver. The same 3 areas analyzed using 100 micron spot tell a very different story. The carbon difference is as large as between 68 and 94%, and actually there is 3 times more silver in area 1 than in area 2. So when you look at all the data from 10 areas and calculate the average and look at this range and standard deviation, you see that averaging over a larger area, which will give smaller standard deviation, and that would lead to erroneous conclusion that sample is more homogeneous than it really is. Because for 100 micron data, you can see a much larger range of carbon concentration, much larger range of silver concentration. So again, comparing the quantification from small and large area is a very useful tool to learn about heterogeneity of your sample. The third tool is using the in situ imaging capabilities. We have access to elemental and chemical images. Different manufacturers have different imaging tools. We have snapshot maps, we can have stage-driven maps. If you have Auger option, you can have access to SEM images. Most of the example that I will be showing today is using secondary X-ray induced images, or SXIs, to locate areas for analysis. So before showing examples, let's go back to the technology behind PHI scanning X-ray microprobe. So in PHI instruments, we are using focused electron beam that creates a small X-ray on a node surface. The X-ray then is being refocused through the monochromator on the sample surface. So when we scan electron beam on the anode, the same exactly pattern and the same size of X-ray as the electron beam will be scanned on top of the sample surface. So in this way, we can produce as small as 10 micron X-ray beam, or we can raster over a much larger area, 1400 micron by, let's say, 300 micron. Secondary X-ray induced electron images is a unique feature of PHI instruments. We are using the same scanning X-ray image, X-ray source. We're scanning over our surface, and we are producing secondary electrons. And this is what is a primary contrast mechanism, is SXi. So this secondary electron yield is related to chemical differences. So we can really easily observe contaminations, patterns, and sometimes we can find defects that are not visible optically. Very similar to a SEM operation, we can navigate using SXi in a live matter by point and click and find areas for analysis. The X-ray source is scanning so fast, it's on the surface, it's really fast, under a few seconds of live image acquisition, that there is no X-ray damage induced by really small X-ray spot that is being used. The unique feature of SXIs is that it allows us to address this question that I mentioned before. How do we know that we are analyzing the data from the area that we would like to analyze it from? SXI are being produced using exactly the same lens X-ray source, and the secondary electron and photoelectrons are measured by exactly the same detection system. So therefore, when we are selecting area for analysis, we have 100% confidence in that we are going to be producing our photoelectrons from the area of choice without any need for alignment. If you are using optical cameras within the instrument, there's always need to align your analytical system and X-ray system to the optical images that you are selecting area for analysis for. This video illustrates this SEM-like approach in navigating using our X-ray microprobe and SXI images. So we can see live image, which is SXI image, acquired from a pattern sample. So it's quite easy to mouse point and click navigation, then for selecting, and you can see how fast it is. But then there is an example of really homogeneous silver foil. So we can see that in this case, our surface as expected is homogeneous. So this is how we can judge whether we can use large area spectroscopy. So when there is no differences in SXI image, it's a good indication that the sample is quite homogeneous. However, we can navigate and we can find another area. So the second area has quite different structures. So we have dark areas, bright areas, and we can see in optical image that there's feature that is caused by this dark spot in SXI image. So when we have this information given to us, it tells us, okay, now we need to understand what is the difference between the chemistry in these areas. So we can save this SXI image as a reference image, and then their stage coordinates will be associated with it. And then we can select points for analysis on bright, on homogeneous, and on dark part of the SXI image. And then these features, as you can see, is on the order of 150 or so microns. So we're going to be using 15 micron X-ray spot to obtain spectra. In this case, the X-ray sources scans from area to area without any stage movement. So it's really accurate and 100% confidence that we are producing spectra from the points that we've selected on the SXI image. And immediately you see that there's different chemistry associated with different parts of the sample that we saw the differences in intensity in SXI images from. So having looked at all of these SXI tools, this is the approach that we usually take and that we recommend. We can use SXI images as an easy, fast way to navigate around the sample and to evaluate the degree of heterogeneity so that then we can determine what type of analysis we should perform, large area or small area. So when you have SXI images that are homogeneous, then your average composition will be representative of the sample chemistry. So you can use high power mode that we called, which is rastering your 100 micron beam over 1400 up to 300 micron area. We can just use spot analysis, or we can use area analysis using the same 100 micron X-ray spot. If SXI images are heterogeneous, then we need to perform small area analysis and from selected points. And for that, we need to select the proper X-ray size, keeping in mind our relationship between the feature size and the probe size of 3:1. Here's another very useful tool. We can use stage-driven SXI map to really quickly survey sample heterogeneity. So here we have a sample which is just a SiO2 film. It's supposed to be homogeneous SiO2 film. We have used SmartSoft, which is our data acquisition package, to generate rectangular points, so 4x4 points that are spaced out 1 millimeter between each other. And then we set up automatic queue to acquire secondary X-ray induced images that are of 1000 micron field of view in size. And then we stitch them together. So here we have 16 images that are covering approximately 16 millimeters squared area in less than 12 minutes. So we can see that there are multiple areas with really high amount of contaminations. So it's a really fast way to understand whether you have heterogeneity. If you are focused on study of heterogeneity, you can know which part of the sample to go to, or if you would like to avoid them, you also can select maybe an area on the sample that is free of contamination. So now that we've talked about these imaging tools, of course, the next step would be to acquire spectra. The goal of us is to acquire high-resolution spectra to learn the chemistry and atomic composition. So we can use those imaging tools to select the area for analysis, keeping in mind our appropriate X-ray probe size. Keeping in mind also that often average concentration does not tell a full story. You may need to report individual atomic composition from selected areas. Here's an example. So we have the same carbon sample with silver distributed on top. So we selected 4 different areas on the sample. So we selected 100 micron spot on two dark areas and 2 bright areas. If we use 100 micron spot effectively, it converts to analysis area of 300 microns. And what happens? It's actually that we're capturing some bright areas in our dark area. We're capturing signal from dark areas in our bright areas. So we are not being selective. However, when we are using really much smaller X-ray spot of 10 microns, effective analysis area in this case is 30 micron, then we're exclusively analyzing bright areas, exclusively analyzing dark areas. So instead of reporting average, you would report atomic concentration from selected areas using 10 micron spot, and that will tell a lot of information about what is the range of my carbon and what is the range of the silver concentration that is observed from area to area. Here's an example where we would like to see whether these 2 samples are different or similar. The first is blind approach. So we selected 10 areas on sample 1 and sample 2. And here's just one of the SXi images extracted from these 2 samples. And we used 100 micron X-ray spot to calculate average composition. So when we look at the carbon concentration for these 2 samples, it's very similar. The standard deviation is also similar for carbon. Sample 2 has slightly more tungsten and iron with larger range. So that's pretty obvious from 100 micron spot analysis as well. However, when we use our selected area approach and we select an area from bright point for sample 1 and dark point for sample 1 and do the same for sample 2, and we use much smaller X-ray spot, 15 micron spot, then we get quite different information. Even average carbon concentration is different, and the range of iron and tungsten detected is quite different. So reporting average composition for this example is inadequate. What you really need to report here is individual atomic concentration from selected areas for 2 different samples so that the customer or analyst will see the range of all of the concentrations from the largest to smallest that can be present in the sample. The last example that I would like to show is the challenges that we don't even think about sometimes when we are doing depth profiles, and especially when the sample is heterogeneous and may have buried defects that you're not aware of. So here's an example of multi-layer coating on glass. We are using monoatomic argon and using 100 micron X-ray spot to extract composition. So here's the depth profile. So we are following really nicely our layers. Then at the end of the profile, we analyze the composition, and this is what we have. We're supposed to have just glass. So the elements in green are supposed to be in glass, but these elements are not supposed to. They have carbon, zinc, silver, tin. These were present in layers. So there are multiple explanations for this observation. It may be that you are redepositing during sputtering those elements. It may be that you have still them present homogeneously distributed on the surface. How do we really know what's going on? Secondary X-ray induced images tells us a lot of useful information. So when we obtain SXI image from the bottom of the crater after the depth profile has been completed, we see defects in the glass structure. So grayish area is our glass, and then we have defects. So when we use small area 15 micron X-ray spot analysis and look at the concentration, we see that indeed in area 1 in the center we have glass, but outside of those defects we have lots of carbon, we have zinc and silver detected. So what exactly is happening? So if we would use 15 micron spot for this analysis, then we would focus only on the part of the glass without defect. Then we would not even detect them. However, we are using 100 micron spot, which is effectively 300 micron analysis area. So in addition to the glass, we are also capturing information from those defects. And that's why we observe really large concentration of zinc, silver, etc. So these acquisitions of SXI images are really useful not only to study your samples as received, but also as you do depth profiling, are very useful, telling you whether there are defects that you may not be even aware of. So coming back to the quote, we have looked at why do we need to use small area analysis. That a lot of the times, due to variation, the signal that we obtained from large area is not average surface composition. So small area analysis, of course, is critical when we have heterogeneous samples. That's the only way to analyze them. If you have defects on the sample or would like to avoid some contamination, it's critical also in analysis of homogeneous samples, as I showed you for the silver foil example. If you're not sure whether you have heterogeneous or homogeneous samples, it's really easy to use small area analysis and to learn the degree of homogeneity of the sample. The tools that we showed here in this webinar always refer to microscopic complementary analysis that is available to you from the same samples. Looking at average composition using different probe size, look at the standard deviation. If you analyze your sample, multiple areas using different probe size and standard deviation is in the same order, it will tell you that your sample is homogeneous. We showed an example of stage-driven map, really fast way to survey large areas on your sample and to find what are the areas of composition that may be different from others. Imaging tools that are available in situ with focus on SXI images because it's probably one of the most powerful features of our instruments. Once we have those images, we can use selected small area approach, and then we need to remember to keep in mind the relationship between the feature and the probe size, that you have always to use 3 times smaller X-ray beam size than the feature that you would like to selectively analyze. X-ray scanning approach is really accurate in providing you with 100% confidence that the signal is being produced from the area of interest in comparison to the stage-driven approach. So that's really a unique feature. And remember that averages don't always tell the story. Report individual atomic concentration from different selected areas to capture the differences in chemistries if the sample is heterogeneous. And finally, I would like to refer you to the resources that we have. We have YouTube channel with videos that we regularly update. The webinar will be posted there. Member area at our website has videos that are training for multi-pack. And for SmartSoft, we have added queue and dashboard training videos. And please follow us on LinkedIn as we are developing new applications that we're publishing papers in collaboration with our customers or have new events and webinars. We are always updating our LinkedIn. And thank you for attention, and please contact us at phi.com if you have any questions.